Jnanam Paramam Dheyam. Knowledge is supreme.
Welcome to this lecture on advanced transition metal organometallic chemistry. As a part of our discussion on transition metal C7H7 complexes, in the last lecture we have looked at the reactivity of this transition metal C7H7 complexes. Of the reactivity that we have looked upon, that involved different kind of reactions starting from redox processes to metallation reactions, to addition of nucleophiles, to even hapticity change, and so on and so forth. So, all of this reactivity is kind of observed in transition metal C7H7 complexes, and that sort of showed that this class of compounds represents a rich gamut of chemistry. Now, there is a little bit more discussion left on transition metal C7H7 complexes, and this is particularly with respect to their bindings. Now, most of the complexes so far discussed for transition metal C7H7 complexes involved eta 7 binding of C7H7 ligand onto the metal center, giving rise to mononuclear metal complexes. However, there are also possibilities in which C7H7 can even bridge between two metal centers, giving rise to dinuclear complexes. So, one such example is illustrated as follows. So, ligand C7H7 ligand bridged dinuclear complex. This is an interesting reaction in which a eta 3 bound iron tricarbonyl compound of the type shown over here in its anionic form reacts with rhodium dicarbonyl chloride dimer, giving rise to this bridging dinuclear heterobimetallic compound. Rhodium so this is an interesting compound in which iron is bound in a eta 3 fashion to iron and eta 4 fashion to rhodium. Now, these both are in 18 valence electron configuration, 6 plus 3 9, 1 10, and iron is 8, so 18, and rhodium also is in 18 valence electron configuration, 4 plus 4 8 1 9 and rhodium is 9, 9 plus 9 18. So, what we see that hapticity of 7 can be split into eta 3 and eta 4, and that can accommodate two different metals, one is iron and rhodium. And not only this binding mode of bridging binding mode of C7H7 ligand is interesting, because C7H7 is split into two binding eta 3 and eta 4. Not only that is interesting, but also it is interesting in the fact that heterobimetallic, two different metallic centers have been stabilized because of this bridging binding of C7H7 ligand. And another interesting fact about this complex is that there also involves one of the rare examples where a metal-metal bond is formed. So, this particular example is kind of interesting in three ways. First, one can see that this C7H7 ligand can indeed bridge, and the bridging can lead to the splitting of their hapticity pattern into of eta 7 into eta 3 and eta 4. Not only that it can bridge, but also it can support heterobimetallic dinuclear complexes. And last of all, there is also interesting metal-metal bond that has been formed in this heterobimetallic dinuclear complex. Okay. This is a very interesting example where the bridging ability of C7H7 ligand has been observed. So, partial coordination of C7H7 leads to metal-metal bond through ligand bridging. So, with this we sort of close our discussion on C7H7 ligands, in which we have not only looked at the various types of complexes that are formed, we have looked at the various methods that are used for preparing these complexes, and also we have looked at the reactivity of C7H7 ligand in details over the last two lectures. Moving on, we are coming on to another new set of ligands, which are C8H8 ligands, or better known as cyclooctatetraene. Tetraene or COT. Okay. Now, COT sort of resembles similarly that of an alkyne ligand. COT can coordinate in a tub fashioned 8 electron donor, or it can coordinate as a planar 10 electron donor aromatic ligand as C8H8 2 minus. Now, this needs a bit of illustration. Now, COT is a cyclooctatetraene, and the structure of that is so this is this 8 electron donor tub shaped structure. This is this 8 electron donor tub shaped structure. The 8 electron donation occurs from here, 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 here. So, there are 4 double bonds giving rise to 8 electron donor. The other possibility of this COT structure is obviously the planar 10 electron donor structure, which is sort of shown over here. So, this is a planar structure which is dianionic, and this is 10 electron donor. Electron donor. So, aromatic planar structure, and stoichiometry is C8H8 2 minus, whereas for this one is C8H8. So, the C8H8 ligand can exist in two binding modes. One can be tub shaped, where it is behave like a tetraene with 4 double bonds, and the other it can be a planar structure where it has 10 electrons and it is in dianionic state. COT displays coordination modes, displays versatile coordination modes, that can be eta 2, eta 4, eta 6 and eta 8. So, depending on the number of atom in the C8H8 ligand that binds to the metal, it can show hapticities ranging from 2, 4, 6 and 8. These is usually for mononuclear complexes, and COT displays eta 3 and eta 5 mode for binuclear complexes. As a result, COT can bind terminally as well as bridging ligand. As a result, it can bind terminally as well as bridging ligands. So, what we see is not only in the structure it shows, but also in its ability to bind to the metal, where it can act like a 8 electron donor tub structure or a 10 electron donor planar structure. It can show a wide variety of binding modes in mononuclear complexes, which can vary from 2, 4, 6 and 8 depending on number of the carbon atoms that the metal is bound to, or it can even show odd hapticity like 3 and 5, and these are specially observed for dinuclear complexes. In addition, COT can also bind as a terminal ligand as well as a bridging ligand. So, really all these properties make a very rich and versatile and interesting chemistry awaiting for us to look into as we discuss more on these special organometallic complexes. So, with that let me start off with the preparation of COT complexes, and depending on the stoichiometry, the different composition of COT complexes for titanium can be observed, and this is illustrated by the examples which are shown over here. Now, the preparations that we are going to be talking about, the planar C8H8 ligands and their complexes. So, the discussion on these few preparative methods would now focus on obtaining transition metal complexes of planar structure of C8H8 ligand. So, preparations. Planar C8H8 ligands. So this involves preparation of transition metal complexes containing planar C8H8 ligands. Now, for these, it is observed that the stoichiometry decides the composition of the complex. And be illustrated by the following two reactions in two different complexes of C8H8 and titanium were obtained. For example, for the reaction of 0.2 TiO C4H9 whole 4 plus 0.4 C8H8 plus twice Al C2H5 whole 3 gives C8H8 whole 3 Ti2. Now, the other stoichiometric reaction is 0.2 titanium OC4H9 whole 4 plus 2 C8H8 plus 2 Al C2H5 whole 3 would give C8H8 whole 2 titanium. So, what is observed over here is the fact that the reaction stoichiometry decides on the composition of the product. Some more examples are shown over here. For example, hafnium tetrachloride plus twice Mg plus 2 C8H8 would give bis complex of C8H8 whole 2 HF plus MgCl2. Similarly, zirconium allyl plus 2 C8H8 would give C8H8 whole 2 zirconium. And lastly, another example involves Cp star or C5Me5, which is also popularly called as pentamethyl cyclopentadienyl ligand complex of titanium Tl3 in the dianic form of the chord, which is K2C8H8 giving magnesium and C8H8 in THF, giving C5Me5 C8H8 titanium. Now, one thing to note over here, that in all of these reactions, these reducing agents like magnesium, metallic magnesium, or over here magnesium C8H8 is added, has been added, and this is primarily to make the chord into a dianic form, which because chord would take 2 electrons to become a dianic form, and that then would react with hafnium. So, in this case, 2 chord in dianic form makes hafnium plus 4 oxidation state. In this case also it is 2 dianic C8H8 making zirconium plus 4 oxidation state, and whereas in this case it is titanium in plus 3 oxidation state, two dianionic as well as one monoanionic C5 minus, but because of this reducing agent magnesium present in the system, that titanium has also undergone a reduction from +4 over here to +3 over here. So, what we see is the fact that this preparation of the C8H8 complexes of transition metal, particularly that of the planar C8H8 complexes of transition metal, involves metal halide as well as some reducing agent and C8H8, which will reduce C8H8 to minus a dianionic form, which will then go and react with the transition metal halide, giving the required transition metal halide complexes. So, here is another interesting example of the synthesis with zirconium salt, and that is illustrated by the reaction discussed here. For example, reaction of zirconium Cl4 with 1 K2 dianionic form of C8H8 and 2 lithium salt of C5Me5 pentamethyl Cp in tetrahydrofuran give rise to this Me5C5 pentamethyl Cp, then dianionic C8H8 zirconium chloride, and that upon reaction with lithium alkyl would alkylate this zirconium, giving rise to Me5C5 C8H8 zirconium alkyl. And if one were to do this reduction of zirconium 4 over here with sodium mercury Hg in toluene, then one would end up with Me5 C5 C8H8 zirconium. To see the oxidation state over here, zirconium is in +4 oxidation state. When one makes this pentamethyl Cp, it's dianionic C8H8 zirconium chloride, then also zirconium is in +4 oxidation state. When the chloride is exchanged with an alkyl to make the zirconium alkyl complex of C8H8 anion dianionic ligand and monoanionic C5Me5 ligand, then overall again zirconium is in +4 oxidation state. However, when the chlorocomplex is treated with or reduced with sodium mercury amalgam to give this C5Me5 C8H8 zirconium, then the zirconium goes back to +3 oxidation state. So, this is an interesting reaction where one can see that the C8H8 dianionic complexes can be formed with zirconium halide in presence of this lithium Cp star salt, giving rise to mixed valence compound which can further be reduced using sodium mercury, or it can exhibit salt metathesis reaction as is observed by treatment with lithium R to correspondingly synthesize the zirconium R derivative. So, then after synthesis we are going to move on to the structure and properties of transition metal C8H8 complexes. And one such example that we are going to be talking about is bis C8H8 complexes. However, the binding of these two C8H8 ligands are quite different, and they bind in two different fashion, one binding in a eta 8 mode and the other binding in eta 4 mode. A very nice example of this is seen for the complex eta 8 C8H8 and eta 4 C8H8 titanium. So this can be illustrated by the structure. So the bottom one is bound in a eta 4 fashion, where the top one is in eta 8 fashion. Eta 8 is planar, whereas this is not puckered. Eta 4 is puckered, and eta 8 is planar, contains equal CC bond lengths of 141 picometer, whereas there is no conjugation across the whole ring in the eta 4 fashion, because it is puckered, so it does not show equal bond length, and this binding is more like a butadiene type. And another interesting bit about this structure is that in solution fluxional structure is observed. Okay. Now another interesting example of this compound is this titanium complex, where this binds in a puckered fashion and it bridges across two titanium center. Something like that, where each of the face, one face is bound to titanium, and then it is bound whereas the other side is also bound to another titanium, and that is bound to another eta 81 compound. So this is mu 1 4 eta 3 6 eta C8H8 eta 8 C8H8 whole 2 titanium whole 2. So this is an interesting compound in which a puckered eta 4 binds to two different titanium. Each of them is then bound to another planar C8H8 moiety. So, with this I would like to conclude today's discussion on our class, and then to summarize, we have started looking at the bridging binding of these eta 7 C7H5 H7 ligands, and which can bind in a eta 3 and eta 4 fashion in a particular example that you have observed to produce a heterobimetallic compound, and not only that, and even that compound had a metal-metal bond. And then we have looked into these new C8H8 ligands that we have been talking about, and what we had seen that C8H8 ligand can bind in two fashion, one in a 10 electron donor planar geometry, in which it is aromatic and it is dianionic in nature, all the CC bond lengths are same, and the other is a puckered binding where it behaves like a tetraolefin and more like a butadiene moiety. And then we had also looked into various synthetic procedures available for preparing these complexes. The ones that we have looked at involves forming planar C8H8 complexes, and these reactions are primarily dependent on stoichiometry. However, the strategy is to take transition metal halides with C8H8 in presence of some reducing agents, which reduces C8H8 to CH8H2 minus dianion and then forms the complexes. We have also looked at some of the structure of these complexes, and in this particular we have looked at two titanium complexes. One was eta 4 CH88 and eta 8 CH88 bound to titanium, and the other one was dinuclear bis titanium eta 4 bound CH88, and then each of the titanium is bound in eta 8 fashion C8H8, the structure of which is shown over here. So, with this I am going to conclude today's discussion on structure and reactivity of CH88 complexes, and then we are going to be taking the more on the structure and reactivity in CH8H8 complexes in the subsequent lecture. I once again thank you for patiently listening to this lecture, and I look forward to take up this topic of CH8H8 ligand in bit more detail in the next lecture to come. Till then, goodbye and thank you.